We are on the cusp of a massive revolution in engineering. Seriously, this is a change as big as going from hand-drawn blueprints to full-on computer-aided design. We're talking about a whole new suite of technologies that isn't just making things a little bit faster, it's completely rewriting the rules of how we invent, create, and build everything around us.
So, let me just start with this question. What if you could design a car, the whole thing, aerodynamics, crash tests, the works? What if you could do all of that not in months or years, but in just a few minutes? It sounds like something straight out of science fiction, right? Well, it's not, and that's exactly what we're going to unpack here. Look, this isn't just a story about faster computers. We are literally watching multiple powerful technologies all come together at the same time to create a totally new way of doing engineering. But to really get how big of a deal this is, we first have to understand the old way of doing things.
For decades, engineers have leaned on computer simulations. So imagine you're designing, say, a new airplane wing. You'd build a digital model of it, and then you'd run a complex simulation to see how air flows over it. Now, this is an incredibly powerful tool, no doubt, but it is so slow. A single, really detailed simulation could tie up a massive supercomputer for weeks. It created this huge bottleneck in the entire design process. So, how do you just smash through that bottleneck? Well, it all starts at the very foundation, a seismic shift in raw computing power. And this isn't just like adding a new floor to the skyscraper of technology. Nope. This is like building on a whole new bedrock, one that lets us build way higher and way faster than we ever thought possible.
Okay, let's put a number on this just to see how wild it is. A single, modern nVIDIA GPU rack. It has the same power as about 400,000 of the standard processors you'd find in a computer. That is like taking an entire warehouse packed full of servers and shrinking it all down into one single cabinet. It's an absolute game changer. And what's really fascinating is how we got here. You see, the performance of traditional CPUs, well, it's seen steady, kind of predictable gains over the years. But GPU performance, that has been an exponential explosion. This massive, growing gap between the two is the key. It's what's unlocking this whole new era of engineering.
But here's the catch. All that incredible hardware, all that power, it's just a really, really expensive paperweight if developers can't actually get to it and use it. You need a bridge. You need a critical software layer to connect the raw potential of the hardware to the real-world applications that engineers use every single day.
And that bridge has a name. It's called CUDA-X. The easiest way to think about it is like a universal translator for the GPU. It takes the incredibly complex, low-level language of the hardware and turns it into a set of tools and commands that any software developer can use, even if they're not a GPU expert.
So, what do these libraries actually do? Well, you can think of them as a toolkit full of pre-built, super-optimized solutions for all the common problems engineers face. So, instead of having to write tons of code from scratch for, fluid dynamics or structural analyses, a developer can just plug in these super-fast building blocks. It instantly accelerates their software, letting them get results in a tiny fraction of the time. Okay, so with this powerful foundation, the crazy fast hardware and the software bridge to access it, NVIDIA has built a 4-pillar strategy that is set to completely transform how engineering gets done. Let's break down how each of these pillars builds on the next one to create something truly revolutionary. And now we get to the really exciting part, AI. But there's a huge challenge. For an AI to learn physics, to actually understand things like airflow or heat transfer well enough to make predictions, it needs an absolutely massive amount of high-quality data to learn from. But where on earth do you get that data? And here is the genius, elegant solution. You use the super-fast GPU simulations we just talked about to create the very data the AI needs to train. It's this incredible virtuous cycle. The faster simulations create mountains of data, which train smarter AI models, which in turn leads to even faster, more accurate insights. The simulations are basically creating the fuel for the AI engine. So here they are, the 4 pillars that make up this whole new workflow. First, you've got accelerated computing to just run those traditional simulations at lightning speed. Second, you use all that data you generated to train AI physics models. Third, those AI models become the engine that powers interactive digital twins. And finally, you have what's called agentic AI, which is kind of like an AI copilot that can help automate the entire design process. See how each one builds on the one before it? It's an incredibly powerful system. So what does this actually mean in the real world? Well, the results they're pretty mind-blowing. A full car simulation that used to take an entire month, now it takes 6 hours. A complex design task that took 70 hours, now it's done in under an hour. And this isn't just about saving time, it's about changing the very nature of design. Suddenly, an engineer can explore and test hundreds of different ideas in the time it used to take them to test just one.
But it's about more than just raw speed. And this quote really hits the nail on the head. You see, raw acceleration, just making the computer faster, that gets you from days down to hours. But it's the AI physics models, the ones trained on all that simulation data, that gets you from hours to real time. And that is a totally different thing. It's not just faster. It's a completely new capability that never existed before.
So, when you put all of this together, how does it actually change the daily life of an engineer? Well, by combining these four pillars, we're not just speeding up the old process. We are creating a brand new one, something that is going to completely redefine what it means to be an engineer in the future.
And it's really important to understand nVIDIA's role in all of this. They are not trying to build the final engineering applications themselves. Their strategy is to build this incredibly powerful platform underneath everything, the hardware, the CUDA-X software, the AI frameworks, and then enable their partners, the big names like Ansys, Siemens, and Cadence, to build their own next-generation tools right on top of it.
And the ultimate goal, the real holy grail of all this, is the interactive digital twin. Just picture an engineer working on a perfect virtual model of a new car. They can literally grab a part of the car's body with their mouse, reshape it, and in that instant, see exactly how that change affects the car's aerodynamics, live. It's like sculpting with the laws of physics. It allows for a level of real-time creativity that was just pure fantasy a few years ago.
So we're leaving behind the old world of design, then simulate, then wait for weeks. We're moving into a new world of design by interacting. So when our best engineers have tools that let them explore thousands of designs in a single afternoon, with an AI basically acting as their brilliant co-pilot, it really makes you wonder, doesn't it? What impossible, incredible things will humanity be able to build next?